from these job-oriented courses or from internships or from risk-fi processor. So in detailly, we are going to see like what are the things we are going to learn in week wise or every module. Okay, so if you have any doubts and all, you can ask here in the session itself. So first we will start with our job-oriented program. Okay. So in the job-oriented program, there will be total 5 modules. Okay. So in each module, there will be regular live sessions. We are going to discuss the projects and protocols are there for each module, and assignments will be provided and mock tests will be provided. Okay. With the materials and tools. So first we'll start with the module 1, the job oriented course. Okay. So here is the design verification course. Design verification job oriented course. So first is the digital electronics module 1. So in the digital electronics, we are going to learn the advanced digital electronics mock test, because as you see, in your undergraduation while you are studying some BTech or MTech, you already know the digital electronics, right? But you don't know how to apply the same theory information, whatever you have learned theoretically, that you want to understand how we can apply into the industry. Okay. Suppose if we are designing a project, means how the digital electronics is involved into that thing we need to understand. And different types of combinational logic circuit. So in theory wise, we know like what is meant by multiplexer or what is meant by a demux or some adders. Okay. But internal functionality is important. Micro architectural level is important, right? So if RTL design engineer is there, so how the RTL design engineer will design a program? So by using the micro architecture of any digital block, that thing we need to understand very clearly. So those things we are going to discuss in each submodule, like a combinational, sequential, registers, counters. So how we can design different types of registers and counters. So logical implementation also very important. Okay. So most of the interview questions will be logical questions only. No to register to design directly a circuit. Okay. So every interview, whatever you are facing, there will be some logical questions. Okay. Suppose how we can implement a multiplexer using different gates, like how we can implement a 2x1 mux using the XOR gate or NAND gate. Okay. Suppose how can we design a XOR gate as a NOT or a buffer? Okay. Like what is the difference between flip-flops or latches, and so what are different registers are there? What is the clock? How many clocks will be required to get the output for parallel communication and the serial communication in the registers? Okay. So different type of registers, counters. So how can we design different modulo counters? Okay, not only modulo counters or some asynchronous or synchronous counters. There would be some logical questions like how can we design multiples of 1 or multiples of 3 or multiples of 5? Okay, some sequence will be given to generate a one time, or two number 2 times, or three number 3 times. So these would be different logical questions. So we need to design the counters according to that. Okay. And next, final state missions. So final state mission is very important thing in the digital electronics, because whatever the project you are taking, whether it is a protocol or a project, so we will design entire design in the final state mission. After converting the design into final state mission, we will write the program. Okay, if you consider any type of protocol like UART or APB or I2C, there will be some flow, right? So how the data will be transferred from the master to slave. So that flow or frame format would be converted into the final state mission. That final state mission will be written into the Verilog program. So that is also very important. and the methods will be there. Like if you consider a melee or mode, so what are the easiest method we need to use according to the industry? Suppose if you consider a melee, it has some limitations due to some glitches and hazards. So why do we use mode? In mode, how can we optimize the final state mission? How can we structurize in a logical way, okay, in easy manner? Okay, that is very important thing we must learn. And what are the different type of memories are there? So if you see everything, we will store the data into the memory, right? The combination of registers or different memories are there, like a RAM, ROM. If you go for more complex way, there will be FIFO memories. Okay, some memory controllers will be there. So different type of memories are there. So that concepts is also important. Additionally, with the digital electronics, we have included static timing analysis. Maybe some of the service-based companies may not ask these static timing analysis and CMOS. But if you go for product-based interviews, if you are from MS or MTech, just they will be asking some few questions, okay, on static timing analysis and CMOS. So that's why we have included these two things. So these two will be discussed in the live sessions only, and different types of glitches and hazards in the combinational logic circuit and sequential logic circuit. Finally, there will be interview preparation. So regularly we will provide the assignment for combinational, sequential, different for all these topics. We will provide the assignments and interview preparation questions. After the digital module, there will be one mock test for everyone. Okay, so this is the module 1. And next, coming to module 2 is RTL design using Verilog HDL. So from static scratch onwards, we are going to start every module. Okay, so if you see in Verilog HDL, first of all, we need to learn what are the applications and what are the different types of data types are available, and what are the different operators and description styles. That means how many ways we can write a Verilog program. If you consider a digital logic circuit, first of all, how can we design a digital logic circuit? There are 4 steps out there, right? So first we need to consider a specification according to your design, whatever the RTL design you want to implement, or if you go some high level, so whatever the project you want to implement, first of all, we meet the requirements of specification, right? So from the specification, we need to take some block diagram for the circuit. Suppose you want to design a multiplexer. Okay, in multiplexer, there are different types, like 4x1 multiplexer or there, 2x1 marks, or some hierarchical marks is there, 16x1 marks, or using 4x1. Okay, so first of all, we are taking the specification. According to that, we will draw the block diagram. That is the first step. From the block diagram, there will be a truth table. So what are the inputs? How many inputs are there? Based on the inputs, how many combinations will get? Okay, so based on the input combinations, there will be output, right? So truth table is necessary. So from the truth table, we are writing some output expression. From the output expression, we can draw the gate level circuit netlist. From the gate level circuit, we are drawing CMOS transistor level circuit. Okay. So whatever the steps we are following to design a single logic circuit in the digital electronics, same way in the Verilog HDL, we can write different levels of programming. Okay. So if you take a truth table in digital electronics, same we can implement in Verilog programming, that is called behavioral leveling, behavioral level. Okay. If you want to write using the output expressions, okay, that would be the data flow modeling. How can we write the Verilog program using data flow modeling? If you take a circuit from the digital electronics, that would be the gate level modeling in the Verilog HDL, or we can call as a structural modeling in the Verilog HDL. Like that, if you want to write a program using the transistor, whatever the gate circuit we are converting into the transistor, if you write the Verilog programming for the transistor level, we call it as a switch level modeling. Okay. So these are different levels of modeling we are going to see in the Verilog HDL. And then, so there are various topics out there internally, like a procedural assignments. So while you are building a code, we need to follow some certain rules, right? So where we can use the sequential logic circuit, where we can use the combinational. So what are the keywords we need to use for sequential? Okay, there are different constraints would be there. So while you are writing some program in any model, so those constraints, certain protocols we are going to look here in the procedural assignment or continuous statements. And one of the main important thing in the Verilog is assignments. So we will assign some right hand side data into the left hand side. Okay. So here we'll get some blocking assignments, non-blocking assignments, serial data execution. Okay. What are the parallel data execution like fork join? So these are different things we are going to learn. Both theory and lab sessions would be combined. So first we will discuss one example theory, and that would be converted into lab session. Same we will do in the lab session. Okay. So next introducing the process of synthesis. Synthesis is nothing but generating the circuit netlist. So tools will be provided. Synthesis tools and simulation tools will be provided. So whatever we are learning, the small things we are developing some small kind of programming, right? So by using some constraints, different topics. So by combining the all those topics, we'll get a complex example, whatever the example or a project. Okay, those things we are going to do the synthesis, and how we can use the tool for synthesis. Different examples we are going to see, and modeling of combinational flip-flop register. So whatever the digital electronic circuits are there. So if you take a combinational, so various nearly 10 to 15 different circuits will be there in the combinational as per our syllabus, right? All those circuits we are going to implement in the Verilog HDL. Okay, regularly there will be an assignment, and same we will discuss in the session also how to implement the marks. So implementation is very easy. Anyone can implement. So as I told now, like a data flow modeling, gate level, switch level, behavioral, everyone can implement. Even if you go in the internet, you will find lot of codes. Okay, but that is not a matter, right? So whatever you are learning, we need to write something in a logical way. Okay, logical coding is also very important in the Verilog HDL. You will be thinking only C language would be required for logical coding and all. No, for Verilog also the logical coding is very important. So how can we write any code in a simple line, just in 1 or 2 lines? How can we implement any multiplexer or any registers or counters? How can we implement in just 1 or 2 lines? Okay, most of the people will write the code in 10 lines, 20 lines also, but that doesn't matter. So how we can write in a very optimized way, in very precise manner, that is very important. If you go for interview also, while you are answering something, how precisely you are writing some code, that is very important. So those things we are going to see mainly in this while we are developing some codes. Okay. Next, after designing the sequential registers, counters, registers also we are seeing different by using the structural modeling, gate level modeling. Counters also we have a lot of examples. Okay, like different counters like multiples of 3, or some sequences. If any sequence is provided, how can we generate the generate the code? These things, these are the good practice examples. And designing finite state missions. So how can we design a finite state mission, like for Mealy or Moore? Any example if we consider, how can we design? So that would be implemented in Verilog. And understanding the simulation cycle, task and functions, how to avoid the simulation mismatches. Like these all are good coding practices. Okay. So while you are writing some code, you will face lot of errors like a syntax errors or some simulation errors, mismatch in the timing. Lot of errors would be faced. So how we can avoid those errors and how can we debug the errors, that is very important. So those things we are going to discuss, and verification constructs and coding style. So what is the better coding style, the good practices of coding, and generating the test bench in the Verilog. So obviously in system Verilog UVM, we will develop the test benches, but Verilog is a basic thing, right? From Verilog only we can develop the system Verilog or UVM. So these also very important. So what are the different system tasks or system functions like a dollar display, dollar write? So why do we use the different system task? So examples of test benches. These things we are going to discuss as a part of Verilog HDL. Okay. So after Verilog HDL, parallelly the assignments would be provided. So the sessions will be live sessions only, right? So there will be one day live session, next day is for assignment practice, and next day is live session, and next like alternate days live sessions and assignments for alternate days. Okay. So after Verilog HDL, we are going to implement RTL design for one protocol, UART protocol, and also one project. So this is up to Verilog. Do you have any doubts up to here?
No, ma'am.
Okay. So next is our system Verilog. So after RTL design, there will be system Verilog. So what is the VLSI design flow? So first in next coming session, we will discuss what is the VLSI and design flow, what are the different fields are involved, and what are the different domains are involved. Okay. So first we have completed the RTL design. Then we need to do the verification. Without doing the verification, we cannot send that RTL netlist to the physical design. Why? Because there will be functional errors. We cannot tell 100% our code will be executed 100% correctly, right? Maybe there will be some signal errors, some functionality errors, or some signal mismatch would be there. So those things would be checked by using the verification. Okay. So after doing the verification only, we can send to the backend process. Okay. So as why we are using these languages like a system Verilog or UVM for verification means, suppose if you observe like a previous like nowadays SOCs, whatever the SOCs we are using, those are very complex, right? The system on chips or any integrated circuit, those are very complex. Okay. So whenever we are designing in a micro architectural level, or thousands of digital blocks will be involved, right? So verification is very tough. In a pre-silicon or post-silicon, verification would be very tough. We need to capture all the scenarios, whatever we are designing, right? So for that purpose, system Verilog is one of the main important language for mainly for dynamic purpose. Okay, so while we are connecting different blocks in an architecture, we need to connect all the data in a dynamic way, right? So that's why system Verilog is very useful because of its features like a OOPS concepts, or we can generate proper randomization. There would be constraints, so we can analyze the coverage also. Coverage in the sense how much design we have covered. That means suppose there are 10 number of blocks in the design. I will draw. So suppose here is the design. There would be a processor and there would be some memory controller, and there would be some like a different graphic processor or some NBIO or SBIO, or some functional blocks will be there, or protocols will be there. Okay, there will be nearly thousands of test cases in each block. More than thousands of test cases will be there. Okay, so in these thousands of test cases, when we do the verification, maybe 100 test cases are covered in the functionality wise. Maybe 100 test cases are covered. Remaining 900 test cases are not covered initially. So how can we get the data whether we have covered all the test cases or not? Here we have the concept like coverage analysis. Okay, based on the coverage analysis, we can check how much data how many number of test cases we have covered, and how much functionality we have covered, and what we need to cover, what are the errors out there. All the things we are going to check from the coverage analysis. That is one of the main feature in the system-based log. Not only that, here if you see all the things like associative arrays, queues, functions, task, interface, virtual interface, polymorphism. So these all the different features in the system Verilog compared to the Verilog. Okay, Verilog is a very basic thing we cannot use for the verification. For complex digital circuits, we cannot do the verification using Verilog HDL. Okay, because of its limitations. When we move to the course, we are going to discuss all these things clearly. So this is about the system Verilog. Okay, we are going to cover all the things here. Next, clocking blocks, the randomization, and class-based random stimulus. So coverage, whatever I have said, we are going to see deep into the functional coverage and assertion-based verification. So system Verilog assertions. And finally, the direct programming interface. So when we want to interface our C language with the Verilog, so there we can use a direct programming interface. And these are different test bench components. So whatever we have discussed till now, like different concepts and all, okay, we need to develop a test bench architecture by using all these concepts, right? So that is the main important thing, how we develop the test bench, how we develop the test cases and the test plan. Whatever the project you are considering, the test plan also very important. That is the main thing every verification engineer must learn. Okay, so that thing we are going to discuss with examples. Okay, after this SP, we are going to implement some projects and protocols in system Verilog. Okay, is it clear up to here, everyone?
Yes, ma'am.
Okay. And next, coming to the UPM. Once the system Verilog is completed, for system Verilog also same, there will be alternate days, live sessions. One day is live session, one day is for assignment practice, and assignments will be provided regularly. Materials also provided, interview questions. So everything in systematic way. Okay, whatever we are discussing, everything would be in systematic. So yeah, after system Verilog, next UVM methodology. So why we are moving to the UVM? There is a system Verilog, right? See, if you go for system Verilog, we need to develop everything from scratch. Okay, so here we don't have any predefined libraries and all. Everything we need to develop from a scratch. Suppose you want to develop a something DMA controller. So we are designing everything from generator. We'll write the program, then scoreboard, then monitor, then driver. Everything we'll develop from scratch. But here in UVM, there will be predefined libraries. Okay, so the functionality of each block, suppose there is a sequence and sequencer. The sequencer would like we no need to write any logic particularly for the component. Everything would be defined inbuilt. Okay, there will be the libraries. So by using the libraries, we are going to develop. Okay, suppose a simply how can we say? Suppose if you want to design a verification plan using the Verilog HDL, maybe it will take 1 year for any simple project. Okay. By using the system Verilog, we can develop in only 6 months because system Verilog is good compared to the Verilog, right? We can write very easily and we can check more corner scenarios using the system Verilog. Like that in UVM, you can complete within 3 months because all predefined libraries are there. Everything we can take from the no need to develop from the scratch. Okay, so that is the advancement of UVM. Whatever the limitations are there in system Verilog, those would be overcome in the Verilog in the UVM. Okay. So first we are going to deep understanding of UVM in SOC level and IP level. So how would we use in IP level and the SOC level, and the detailed explanation of UVC, Universal Verification Component, in the SOC and IP. And we are starting from scratch. So what are the features? What is the test bench hierarchy? What are the components? And what is meant by sequence item, sequencers? So different phases, driver, how we can create a driver monitor. Already you will be learning all these things from system Verilog. Just syntax differences will be there. Mostly system Verilog would be covered in UVM, but small syntax differences will be there. The coding style is different. Okay, because here we use all predefined libraries, and some phases concept is there. Some factory registration concept will be there. So only small differences would be there. So finally, how can we create the TLM ports, RAL model? These are internal concepts. So finally, how can we create the different test examples, test bench, the test plan? So according to our feature, so these things we are going to discuss. And here, if you observe importance of regression, how to run the regression, all these concepts are some additional concepts from the SOC verification. We just added some additional concept. So how can we check either test pass or fail? Anyway, while we are writing the test cases and all, you will find how to debug the error signatures and all. So these are the different topics we are going to cover in the UVM. Okay, is it clear, everyone?
Yes, ma'am.
So coming to the projects, the main important thing. So what are the projects and what are the protocols we are going to discuss? So here is the RTL design for your protocol, and we are going to implement in detail architecture. So next, 4-port calculator implementation using Verilog HDL. Those two, one project, one protocol, Verilog. In system Verilog, I2C protocol implementation and Verilog. And so AMBA protocol, AMBA APB in system Verilog. Okay. Next, coming to UVM, 1x3 router project in UVM verification. So detailedly we are going to discuss like how we develop the test plan, how to write different test cases, and then RTL design of 4-port calculator in UVM, and DMA controller with the coverage analysis, RTL design and verification. AHB AXI is covered in UVM. Okay. So these are the different projects and protocols. And finally, Perl scripting language. So in Perl also we are going to discuss on how to run the commands, and different concepts are there, like data types, hashes, loops, operators. So how can we extract some coverage report, or how can we run n number of test cases using Perl scripting? So here we use the Linux for Perl scripting. So those tools will be provided. So here we are providing Quartus Prime model simulator and Xilinx Vivado tools. Okay. So do you have any other doubts up to here?
No, ma'am.
Okay. And next is advanced verification course is there. So if you know already Verilog HDL and all, you can prefer with the advanced verification course. And we have launched the internship, right? So what is the difference between internship and the course? In the sense, internship means self-learning. So everything is same, course module is same, system Verilog, UVM, Verilog, digital electronics, everything is same. But for training means there will be regular live session. As I told now, alternate days. So whatever the topics are mentioned here, everything we are going to discuss in a live. Okay. But internship means it's a self-learning program. Okay. So we will provide the materials, assignments, and we will assign the task. So regular task or weekly task. So what you need to complete in particular week. So you need to learn that thing you are born, but we will provide the assignment materials, right? So you need to learn your own and you need to practice the assignments. Okay. And remaining all are same. Mock test will be given, tools access will be provided. But there will be no regular live session. Weekend doubt discussion sessions will be there. Weekend live doubt discussion sessions will be there for internship. That is the only difference. Okay. So if you go for advanced verification course, this would be started only from systemware log. Okay. Systemware log and UVM and scripting. So this is the advanced verification course and these are the projects. Okay. So next is risk file. So another course that we have launched is Risk5. So I think some of you are there for Risk5 processor also. Okay, let me discuss this thing also. So actually, if you see the name here, 32-bit Risk5 processor integrated into system on chip. Okay, so what is the main intention of this course means? There would be a system on chip, right? So what is mean by system on chip? What is the difference between integrated circuit and the system on chip? Integrated circuit means all the blocks would be connected on a PCB board, like a motherboard if you see. System on chip means we are integrating all blocks on a single chip. Okay. So here there would be a processor, central processing unit or graphic processor is there. Some memory controller are there. Some subsystems will be there. Different type of peripherals would be there and different type of high speed communication protocols or some bus protocols. The ports would be there in the system on chip, right? So suppose this is the processor. We are going to develop this one, not developing. We are going to design that RISC-V processor. Okay. So another thing what we have added in the course means I didn't mention here in the curriculum, but I have added 32-bit RISC-V processor integration with the DMA controller, memory controller. Okay. So we are taking two particular IPs. One is RISC-V processor module. Another one is memory control module. We are going to design both RISC-V and the memory and we are going to integrate. Okay. Can you please join for the next session quickly? Because the session is limit 40 minutes. Using the same link, you can join again. Okay. Can you join quickly using the same link? Okay. So as I told that, so we are in the SOC, we are considering one RISC-V processor. So there are different processors like from Intel company, if you see x86 processor. So RISC-V is from ARM company, right? So RISC-V. So we are going to start from everything from scratch. So the evolvement of processor, difference between x86, RISC-V and CISC processors. So everything we are going to discuss from scratch. So the main intention of project means I will show you an example. So this is the SOC, if you consider a simple system on chip architecture. Okay. So in system on chip architecture, there will be different blocks, central processing unit or digital signal processing or some graphic processing unit. So this central processing unit have different processor, like a different cores would be there and the different threads or some cache memory would be there. So that processor would be interacted with the direct memory access control. So this is one IP, this is another IP. So we are going to interface this CPU with the direct memory access. So first we are going to design RISC-V processor, then we are going to design the memory, direct memory access controller, DMA. Both we are going to interface. That is the main intention of this project. But I didn't kept here. So I need to update this brochure. So that is the main intention of the project. Okay. So what we are going to discuss here. First module 1 is SOC level verification. Okay. So here we are going to discuss about ASIC versus FPGA. Actually, already this module is completed. First module is the difference between ASIC and FPGA, SOC architecture. So what are the different blocks involved in the SOC architecture, and each functionality of each block, and the different teams involved in the SOC verification, and the flow of SOC verification, difference between IP level verification, SOC, and subsystem level verification, and overview of the SOC level verification. So this is the module 1. And from here, the main module is going to start. Okay. Because when you are designing some disk file, we need to know the overall thing, right? So we cannot go directly with the risk file. So what actually happening in the SOC level, in the IP level, so how individual IPs would be connected, we need to understand that thing. So that's why we have just integrated into like designed like with SOC. Okay. So in the main module, we are going to discuss history of RISC-V processor, like how the evolution, like a difference between von Neumann architecture and different processors. Next, overview of instruction set architecture. So the pipeline architecture. So micro architecture of pipeline also we are going to discuss. Okay. Actually, you won't get anywhere the micro architecture of pipeline. Just you will get the information like what is fetching, decoding, execution, memory, write backstage, only that block diagram. But we are going to discuss internal micro architecture. Mostly, I'm going to use the computer architecture and computer organization concepts here, like interrupts, okay, error handling or error exceptions. So these things also I'm going to involve here. So we are going to discuss the pipeline architecture, internally micro architecture, and the instruction set. What are the different instruction sets, like immediate type or register type or some branch type, jump. So all the instructions we are going to discuss, and what are the register and instruction format. Formats also very important. So assembly language programming is very important. So we are going to practice the assembly language programming. There would be the assignments, interview questions would be there. So finally, the detailed explanation of data hazards, control hazards. So hazards also very important, because processor time should be is very important, right? So we need to check always the speed of the processor, how much speed it is working, the clock frequency and the CPI. So based on the CPI, if we increase the CPI, so what are the hazards would be occur? If we decrease the CPI, so what are the limitations would be there? So how can we manage the CPI? Okay, clocks per number of clock per instruction. So those things we are going to discuss with the control hazard. Different topics are there internally, subtopics would be there, and the control hazards. And mainly assembly language programming we are going to practice, and execution stages, and ALU data path. So whatever we have designed instruction set in the micro architecture level, those would be converted into the digital circuit. In the sense, we need to write the Verilog programming, right? So how can we write the Verilog programming? There must be some digital circuit with registers, ALUs, and all. So we are going to design the each instruction in a digital architecture, in a micro architecture. That architecture would be designed in a Verilog HDL. Okay. So finally, RTL design of RISC-V processor. So there would be a microarchitecture for all the instructions. By using that, we are going to design the Verilog programming. That is very complex thing. So we need to check all internal blocks. There would be a lot of Verilog files would be there. So that is very complex. And finally, we are verifying the RISC-V processor using SV or UVM. And then separately, we are designing the DMA controller. With the DMA controller, we are going to interface the RISC-V processor. Okay. So that is the main intention of this project. And finally, module 3 is the pre-silicon and post-silicon at SOC level. What are the different teams involvement is there? What is the post-silicon debugging? So these are the different topics in SOC level. So what is mean by DFT? So DFT versus DFT. So in pre-silicon, what is the importance of DFT, and post-silicon, what is the importance of DFT? And how can we develop the test plan? So anyway, we are writing, we are going to verify using system verilog and UVM, right? So there we'll see how to develop the test plan and how test cases are created. And these are different extra topics we are going to discuss, like C++, how can we use for CPU verification. So if you see processor, we are designing using the assembly language programming, right? Instruction set. So those instructions we cannot verify using the system verilog or UVM, because SV or UVM can be verified for only HDLs for verilog. Okay. We cannot verify for C or C. We cannot verify for assembly language programming. So for that instruction verification, we use the C or C++ in industries. Okay. So we are going to see that thing. And what are the main steps we need to follow for debugging the error. So here also we are going to discuss about the regressions, how to run the regressions, and so how to check the test pass, fail, error signatures. So these things we are going to discuss. Another thing is I'm going to add the graphic processor unit, GPU architecture, and how can we design the GPU in this course. Okay, because last week while I'm discussing the SOC verification, same here, I got some queries like how we can design the GPU. Is it same as a CPU, like a RISC-V, or is it different? So those things I'm going to discuss in this separately. Okay, so these are the three courses are there. Full-time job-oriented courses and internship. So internship is also same as I told, but there will be no regular live sessions for internship. There will be only doubt discussion sessions, and remaining all same. Okay. So if you have any doubts and all, you can ask your doubts now. Do you have any doubts?
No, ma'am.
So what?
No, good.
Yeah.
Right.
Recorded sessions will be provided. If you miss any session, the recorded session will be provided. Or if you don't understand any session, we'll provide the recorded. Okay. So, yeah, you can ask your doubts still. And another thing is we have changed our rules. So mostly we are concentrating on practical things. So while we are, even it is online, we need to on our camera. So video must be visible, trainer video, and from mentor side and from your side, okay, from student side. So then we can focus more on what we are going to discuss, right? So assignments you need to submit within a time. There would be 1 week or 2 weeks duration for submission. So yeah, is there any doubts, or shall we close the session?
For internship, like actually, I spoke to you. I informed you about the projects. Like I want to do important project for my MS, like on RISC-V. So how can I uh, initially start with it, like uh, with the RISC-V project?
With the risk five, initially, how can we start? Means, anyway, we are going to take the live session, right? So you are
Mm.
going to join for the live sessions. So first, we will start understanding with the architecture level. So pipeline architecture is important, first of all. So in the pipeline architecture, so what are the different blocks involved? Suppose fetching is there. So how we are fetching the data? There would be a program counter, there would be an instruction block would be there. So how we are fetching the data from program counter? So what is mean by byte addressing? In RISC-V, mostly we use the byte addressing. So how we are fetching the data? So internal architecture we need to understand first of all. So and then uh, so how we are writing the assembly language programming using the instruction set, that thing you need to understand. So whatever the architecture is there, that would be converted into the data path. So from the data path, we need to write the program. So this would be the,
So assignments will be given parallelly, like
yes,
whenever we are.
assignments would be given parallelly. So whatever the session is completed today, for RISC-V, there would be weekly assignment. Normal
Okay.
design verification course, there will be regular assignment.
Okay.
Yeah. Okay. Any other doubts?